Hi, my name is Jari Hannu. I'm Adjunct Professor and a University Lecturer here at the University of Oulu, working in the Microelectronics Research Unit. I mainly work with education, but also have done some research with our research team here in the Microelectronics Research Unit. Most of the things which we're presenting here are mainly done with our researchers, Jarkko Tolvanen, Niina Halonen, Sakar Palario, Ahmed Albelaki and Sepide Kasrei. Also, our former thesis worker Joni Kilpijärvi has a big impact on the things which I'm presenting now. And also a lot of people from the Microelectronics Research Unit and also some of the students of our degree program have been part of this research which I'm presenting. I have a couple of different subjects here. First, I'm going to start with what kind of things you can do for sensing people from cell level to skin level. One thing which we started here, this is mainly was our researchers with cooperation with the Linköping University in Sweden. We were studying how to detect different kind of cells, different kind of biological things, and we were developing this kind of CMOS chips which can detect cells. So in the green picture there you can see that there's a sensor kind of element there which is 30 micrometers long. It's a capacitive sensor, and if you have different kind of cells or different kind of defects there, it can detect them quite easily. So it was a big matrix. There's a lot of those, and we did measurement with those, we did packaging, and we did different kind of things with Linköping. It went quite well. That made us to think, is there any other way which we can do this? And we continued. This is kind of radio frequency sensors. So we did the same kind of detection on these radio frequency devices. So could we use higher frequency elements for detecting, for example, cells? So if there's cancer cells, they have different kind of response, or healthy cells in there. But also we were studying, is there any other properties here we can measure? Is there, for example, blood? It has different kind of components in there. So they have acidity there, different kind of natrium, chloride kind of compositions there. So we did this kind of resonator structure here, which you can detect really small changes about the blood pH level or like the salt levels on the blood. And it was working quite nice. So that way it made us also think what we can do other things with the sensors, and we wanted to simplify our sensor. This was this kind of a capacitor structure here which we had. So we were discussing, can it be a simpler one? And we made this kind of a resonator structure, which is kind of nice round one. You can see in the top left picture there. And we were measuring skin. And from the skin, we wanted to know, can you detect different kind of things? For example, dehydration was a problem, which can be, well, a problem, for example, for kids or older people who cannot detect have they drank enough water. For example, there's a really hot day and you lose a lot of water because of the environment. So this kind of sensor which we made could help to detect that you have lost a lot of water from your body, and you can see it from the skin. So in this, we made the sensor, we made the measurements with the radio frequency devices, so the resonance frequencies was somewhere more than 5 gigahertz. And those measurements, we also made this kind of portable device on there. And the measurements were mainly made with phantom materials, which we developed ourselves. That was fun to make, different kind of permittivities and different kind of losses, which we're able to implement on models of skin. And there's a lot of potential here. Now the research in this is a little bit on kind of waiting. Let's see if we get new possibilities in there. So those were the measurements which we could do from the cell level to from the organ level. So like a long kind of string of different kind of things which you can measure. And there are, of course, different kind of measurements which we are doing all the time. So measuring human is a big possibility, especially on ICT. There are a lot of wearable devices and a lot of sensing to be there. One of the problems in wearable devices that they are quite bulky. The other thing which we were focusing on there is how to implement sensors and electronics there to be stretchable. And that was the first thing which we started also was the sensing elements. So here you can see on the left there's a small sensor. It's a resistive sensor which was made on really highly stretchable device. This device which we used was able to stretch 75%, so nearly double the device itself. And it was really sensitive to different kind of stretching. So it can detect really small changes, but it can do really big changes in there. This could be also machine washable, so you can integrate this kind of sensors to your clothes, so you can measure and wash those devices if they are attached in the clothing. There's single level which you can measure. So, for example, you can measure easily the breathing. You could also measure the pulse levels which you have in your blood vessels. It can also detect different words and different kind of things from your throat quite easily, and measure, of course, different kind of movements on your body. So it's a resistive sensor. It can measure strain, pressure, and vibrations, of course. So that was the first step which we took on this kind of stretchable sensors. And then the second step was to get more out of it. So we used this bio-based carbon materials and made this sandwich structure with different conductive layers. And then we had this composite material which is stretchable and really, really durable in many kind of things. It was a dual sensing device. So it can measure stretching and pressure with capacitive functions, but it can also detect really switching in there if you compress it enough, so you can detect resistive changes. So it had these dual things to measure, which can be utilized in many kind of different wearable devices. And this was also really, really stretchable kind of material also. I think it was something like 75 of 100% of stretching which was able to do with this device. Another step from this device also was to do a device which has more properties there. So it can measure stretching, pressure, but it also can measure proximity, so it can detect if something is near you. This was using similar materials, but we were more focusing on the structure in here. So in the picture below you can see there's a capacitance change in there and the resistance change which you can do. So if there's elongation, you can change the capacitance quite easily. If it's a static hold, it stays static. If there's pressure, it can have a resistive response. If you have a proximity there, you can see a little bit wave in there in the figure, the capacitance changing, and then you release the elongation there, you can have again different kind of response in capacitive there. So also two functions, two different kind of electrical properties you can measure, and well, many functions you can actually measure with these devices. We are continuing this work. We have this project called SEHU. This time we are focusing on different kind of mechanical sensors, radiation sensors, and trying to focus on components which are, if you have deformation there, so they for example, the radio frequency devices are insensible for that. This is one thing which our doctoral student is now working on. It's a strain-insensitive temperature sensors. So we wanted to do temperature sensors quite big size for skin measurements, for example. So if you have a sensor on your skin, you want it to be feeling mechanically soft, so it doesn't feel uncomfortable. So we developed this big sensor. It's possible to have in many different kind of places in your body, and it's able to measure the temperature. So the skin temperature, that's the main target with us. But the interesting part is that we wanted to measure the temperature even though it's stretched. We wanted to know because the stretching itself affects the electrical response, and also the temperature itself affects the electrical response itself, mainly resistive kind of device which we are having here. And the first publication is now under work here. It's going to be published hopefully quite soon. And it seems that we can do really a device which is really stretchable, and it's really good kind of temperature response which it can provide. Another thing which is working on this project is also flexible, stretchable transistors, the built transistors which you can have as a part of devices or also sensing elements. So just doing basic work in the transistor side. One of the things which we try to implement is self-healing materials with the transistor, trying to produce all the materials which are there to be self-healing. This is an example what I was discussing about self-healing. When you have really stretchable devices, the durability is another thing which you want to have on those devices. The mechanical wear is quite a lot. We wanted to also study if you have this kind of wearable devices, so how to make them as reliable as possible. There's an example here of a sensor element, which is a reflective sensor. So if you cut it, it heals itself. And this healing is done under cold water. And the material which we have developed has been dielectric materials, conductive materials, different kind of reflective materials. And you can really have self-healing systems on your devices which you have. And these are really promising materials, what we are doing. Also, bio-based materials have been quite important for us. So, for example, we have developed emission shielding materials. For example, if you have radiative things and you want to have areas where there's no noise coming from the radio frequency signals, emission shielding materials are really good in this way. We have used lightweight carbon nanocomposites and then added biodegradable carbon materials in there, which you can use for having really effective shielding for different kind of radio frequency signals. Also, you can use these bio-based materials in many different things. For example, the sensor, which I was showing first, the stretchable sensor, was part of this. This is one of example we were using. We had these conveyor rolls used in factories to have small parts coming, and they wear a lot, and you have to change them all the time. So instead that you change them all the time, periodically we wanted to see can you measure those beforehand. And we used these bio-based materials as protective material in there. And when we had the composite having the carbon material in there, we could do measurements and see quite easily that is the material wear enough or is it still usable for a longer period. Also, of course, the materials can be used in many parts, like we had this NewPack project where we used bio-based materials to make plastics. So it's a really big part of the circular economy trends which we are doing. And for our part, we try to utilize these in electronics substrates and different kind of components for the new kind of devices which might be in the future. Also, in the end, I just wanted to add a couple of other ideas which we have been working on. For example, this kind of a smart mask was one part. During the COVID, there was a lot of research in different kind of things. So the smart mask was one of the things which we were doing. And we were mainly working on the mask itself. And we wanted to have different parts in there to be usable for long term, and of course can you add sensing in many things. So we had commercial sensors there. They were carbon dioxide, temperature sensor and that kind of things. But we also added, for example, for the straps which go under your head, those we tried to sense so you can detect is the mask really sitting well on your face and that kind of things. So it was a COVID research which you could do easily. One more science fiction idea which we have was this kind of programmable appearance. This came from movies like the Iron Man over here. So how could you build material which can change its shape in your environment? In the left you can see there are a lot of this kind of concepts. So you could change, for example, the size of the pool which you're using, or you could add differently, for example, shelves on your shelves and many of these kind of ideas. So we tried this and checked what do you need and how you can do it. And we had this small project called Programmable Appearance. So we tried to modify the shape and the color of the system by changing the material properties. It was basically based on, we had this matrix polymer, which is activated by heat, and also magnetic fields, which we're using for move the systems in there, and also color changing materials, for example, so you can see when you're modifying the appearance and is it suitable for modifying and that kind of things. We made the first demos or demonstrations that it's usable, okay, but it requires quite a lot for many kind of different things. So really focused temperature changes, really focused magnetic field changes. So these will be working on. And hopefully in the future we will find a new application for this. That was my short presentation about the research which we have done at the Microelectronics Research Unit, mainly about wearable sensors, but also a couple of other things considering electronics materials and their usability in different kind of applications. I hope you enjoyed it.